Hello everyone, welcome to pre-algebra. In this lecture, we're going to look at signed numbers. So we're going to start module 7 and look at signed numbers, meaning numbers that are both positive and negative, and how to operate with signed numbers. In this section, section 7.1, we're going to introduce signed numbers, define a few things, and then in subsequent sections, we will actually look at the operations. So the way I want to start this is I want to review the different types of sets of numbers that we are using in this class. Some of these we've already talked about, and some of them are going to be new. So let me describe these. So there's different sets of numbers. Okay, the first set is simply the counting numbers, right? So remember, that's 1, 2, 3, 4, ... means it goes all the way to infinity. And these are actually called the natural numbers. So you can think of them as the counting numbers. Okay, then if I go up a little bit, so a slightly larger, it's really the same size in terms of infinity, but there's an additional number added to it. A slightly larger set is the set of whole numbers, which we've already talked about, right? Remember, it's all the natural numbers plus the whole numbers also include 0. Right? So the whole numbers, and we spent the entire first chapter, right, just talking about the whole numbers. So I'll just say it includes 0. Okay, then to get a little bit larger, we include all the whole numbers and then all the opposites of the natural numbers. So like -1, -2, -3, -4, ... and that goes to negative infinity. These are called the integers. So I'll just write, it includes the opposites of the natural numbers. Okay, and notice each set is slightly bigger, right, than the previous sets. Okay, the next set of numbers, again, we've talked about these some, are what's called the rational numbers. These are really the fractions, right? So let me write down the definition. So rational numbers are numbers that can be written in the form a over b. So really you can think of them as fractions, where a and b are integers, and we have the restriction that obviously b can't be 0, right? Because again, we can't divide by 0. So b can't be 0. So the other way to think about these is they are our fractions. But now we're going to include negatives, right? As well as just before we talked about fractions where we just had a whole number divided by a whole number. Now, in general, a rational number is really an integer divided by an integer. So the fractions could also be negative. Okay, here's an interesting thing about rational numbers. When expressed in decimal form, So if I convert them to a decimal, rational numbers either terminate or repeat. So rational numbers they do two things. Or one of two things. They either terminate or repeat. Okay, so what does that mean? Well, let's look at an example here. Let's say I have some rational number, say 3/8. Okay, so we can convert that into a decimal value, right? How do we do that? We just simply divide, right? So I would do 3 divided by 8. My decimal point is right there after the 3. I don't have to move it at all, right? No adjustments, but I better put some zeros in here. And I know in the answer, in the quotient, the decimal point is going to pop up there. So let's actually divide this out. So 8 goes into 30 how many times? Well, it goes in 3 times, right? Then 3 times 8 is 24. I subtract, bring down the next digit. 8 into 60, that's going to be 7 times. 7 times 8 is 56. Subtract, bring down the next digit, which is 0. 8 into 40 is actually exactly 5, right? 5 times 8 is 40. 0. And then after, if I were to keep going, these would all be 0 now. Okay? Dot, dot, dot. So this is what we mean by terminates. It stops, right? So when I divide this out, I get 0.375, and then it stops. Everything else is 0. So that's what we mean by terminates. So in this case, this fraction, or this rational number, terminates. What's an example of repeating? Well, let's say I have another fraction, let's say 2/3. So if I convert this to a decimal, let's divide this out. 2 divided by 3. So 3 goes into 26 times. I get 18, right? Subtract 2, bring down the next digit, 0. 3 goes into 26 times. 6 times 3 is 18. Subtract, bring down the next 0. 3 goes into 26 times. And notice here, I'm going to keep getting, right? I'm going to keep getting a 6 here. So that goes on forever. So that's what we mean by repeat. So the 6 in this case repeats. And the way to denote that it repeats is, remember, we put a bar over the repeating part. In this case, it's just a 6 that repeats. So I put a bar over the 6. And that means 0.666666 forever. Okay, so this would be an example where I have a rational number, and when we express it in decimal form, it repeats. So that will always be true. If you have a rational number, it's either going to terminate, like 3/8 did over here, or it's going to repeat, like 2/3. Those are the only two possibilities. Okay, well, are there numbers that have decimal expansions or decimal representations that neither terminate nor repeat? Yes, and those are called irrational numbers. So let me discuss that a little bit. So irrational numbers have decimal expansions or representations, I'll say expansions, that neither terminate nor repeat. Okay, so at first you might be thinking, well, what's an example of an irrational number? There's one that we're going to definitely look at when we get into the geometry chapter, and you may have heard of this. It's pi right? It's the ratio of the circumference to the diameter of a circle. It's very important. And we know it's approximately equal to 3.14159, etc., dot, dot, dot. But it turns out that if you do the expansion out, it never ends, right? So it never terminates, and it never repeats. So pi would be an example of an irrational number. Another example would be something like, say, square root of 2, right? As long as it isn't a perfect square, like square root of 16 would be 4. So that's just a whole number, right? That's a rational number. Square root of 2, in this case, is not. It starts off, it's around 1.41, dot, 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 and it never ends, and it never repeats again. So that would also be irrational. And it turns out that there's an infinite number of irrational numbers. So there's many, 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 many of these. And in actuality, there's an infinite number of rational as well. And it turns out the size of the infinity of irrational numbers is larger than the infinity of rational numbers. Okay, we don't really have to go into that in detail, but just realize there's an infinite number of irrational and an infinite number of rational numbers. Okay, so for example, if I give you this problem, is this number is it rational or irrational? So I have 0.33, 457, 457, 457. The dot, dot, dot means 457. Right? It's going to keep repeating. So because it's repeating, this is a rational number, right? In fact, another way of writing this is this number is 0.33. That part doesn't repeat, but then the 457 repeats, so I put a bar over the 457. So it's rational because it repeats. What about this number? So this number is 0.12, 122, 1222, 12222, and dot 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 means the same pattern holds, right? 1 and then 5 twos and 1 and 6 twos and so on. Well, there certainly is a pattern here, right? It's a 1 followed by 1 2, 1 followed by 2 twos, 1 followed by 3 twos, and so on. But it never terminates, right? It never stops. We don't just get a bunch of zeros at any point. And it never repeats. There's a pattern, but it doesn't repeat. So if it neither terminates nor repeats, what kind of a number is this? It must be irrational. So this number is irrational. Right? It neither terminates nor repeats. Okay, so putting this all together, it turns out that if we include the rational and irrational numbers together, we call that set the real numbers. So the real numbers include the rational and irrational numbers. Sometimes I'll illustrate it like this with like a tree diagram. So here's the real numbers right up at top, and they include the rational, so like all of your fractions, and then irrational, These are numbers that can't be written as a fraction, right? Remember, irrational can't be written as a fraction. And if you put them in decimal form, they neither terminate nor repeat. And then we could go further here on the rational. The rational, in some sense, include, right? They include the integers. It's like a subset. Then the integers include the whole numbers. And the whole numbers include the natural numbers. Okay, but the important point is that it's really, when we talk about algebra or even more advanced math, really mostly you're going to be working with the real numbers. So the set of real numbers is very important. Okay, how can we represent real numbers? Well, we can use what's called a real number line. So all real numbers have a location, right? A home, a location on a real number line. And what is a real number line? It's basically a horizontal line that represents all real numbers. But what we do is we typically only represent the integers, and we start with at 0, right? And then if I move to the right, that's going to be positive. So I'll just put a couple tick marks here. These are just going to be the positive integers. So to the right is positive. And if I go to the left, I'm again going to represent just some of the integers. Remember, this goes on forever. I'm just showing some of these. So let's say -1, -2. So these are the negative integers. So to the left is negative. And every real number has a home somewhere on there, right? So, for example, let's say I give you the rational number, say 6/3, right? So 6/3. Well, that's really just 2, right? It simplifies to 2. So that has a home on the real number line right here. Let's say I give you the number 1/2. Well, that has a home right here, right? Between 0 and 1. So right there would be 1/2. Let's say -pi, right? -pi. Well, that's around -3.14. So that's going to have a home right here between -3 and -4. -5/2. Well, that's -2.5, right? Or -2.5. So that's going to be right in between -2 and -3. That will have a home right there. Okay, square root of 9. Well, that actually is a rational number, right? Because in fact, it's a whole number. It's just equal to 3. So that has a home right here. Square root of 2. Well, remember we said that was around 1.41 ... and that one's irrational. But it has a home somewhere. Not quite 1.5, so 1.4, say right there. Etc., etc., etc. So all real numbers have a location on that horizontal real number line. Okay, so it's a nice way of representing all those real numbers. Okay, I want to introduce a few more concepts here. First one is something called opposites. Let me do a new page. So let me define it first. So two numbers that are the same distance from 0 on the real number line, but on opposite sides of 0 are called opposites. So two numbers that are the same distance from 0 on the real number line but on opposite sides of 0 are called opposites. Okay, now the key word here is distance. We have to understand what distance means. Distance is always going to be a non-negative value, right? It can never be negative. It could be 0, or more typically it's going to be a positive value, okay? So let me write that down. So distance is always non-negative. Meaning it's 0 or greater, right? Okay, so let's actually write out some numbers and then we'll find their opposites. So I'll make a little table here. So number, and then I want to find the opposite. So let's say the number is 3, right? If I have a real number line, I'll do it right above it. Oops, -1, -2, -4, -5. And again, it goes on forever, right, in both directions. So where is 3? Well, 3 is right here. And how far away is that from 0? Well, it's 3 units from 0. So what number on the other side, on the opposite side of 0, is also 3 units away from 0? Well, that number must be -3, right? This is also 3 units. So the distance here, we don't care about negatives in terms of the distance. The distance is just 3 units. So the opposite of +3 is going to be -3, because it's the same distance from 0 on the other side of 0, right, on a real number line. Okay, if the original number was -2 1/3, so let's say right here. I have to split this up into thirds, right? So it's like right here. So what number on the other side is, so this distance would be 2 1/3 units away from 0. What number on the other side is 2 1/3 units away from 0? Well, it must be +2 1/3, right? So if my original number is -2 1/3, the opposite must be +2 1/3. So you can see here, really to find the opposite, all you have to do is keep the same number and then change the sign. So if your original number is 7/2, which by the way is like 3.5, like right here, the opposite must be -3.5, right? -3.5. So in this case, we'd write it as -7/2 because we're keeping it as a rational number, as a fraction. If your original number was -pi, what's the opposite? +pi, and so on and so forth. So really all we're doing is changing the sign, right, to find the opposite. Okay, another important concept is something called the absolute value. So let me give you the definition. So the absolute value of a number is its distance from 0 on a real number line. Okay, so for example, if I wanted to find the absolute value of -4. So the way that we denote absolute value is we use these two vertical bars here, two vertical lines. So that means absolute value of -4. So where is -4 on a real number line? That would be right here, right? This would be -4. All right, I'll put in a few integers here. So 1, 2, 3, 4, -1, -2, -3, -4. And what is its distance from 0? Remember, distance doesn't care about signs. It's always going to be non-negative. So how many units from 0 is -4? It's 4 units away. And the definition of absolute value of a number is its distance from 0. So absolute value of -4 is just going to be 4, right? It's 4 units away. If the number were, say, 3, absolute value of 3. So 3 is right here. So how far away from 0 is 3? Well, it's 3 units away. So absolute value of 3 is just going to be +3. If I have absolute value of -2.5, how many units away from 0 is -2.5? It's 2.5 units. So notice what's happening here, right? If you take the absolute value of a negative number, it makes it positive, right? It's the same number, but it becomes positive. If you take the absolute value of a positive number, like absolute value of 3, it stays positive, right? It doesn't change the sign. So all the absolute values are always going to be non-negative. Let's do a few more of these. Absolute value of -pi. Well, that's going to be +pi, right? What about absolute value of 0? How far away is that from 0? It's 0 away, right? That's the only one that could be 0. All the other ones are going to be positive. One thing you have to be a little careful with is, what if I have negative absolute value of -7? What is that? Well, we have to do, forget about that negative for now. Just look at the absolute value of -7. We know that's going to be +7, but then this negative has to be applied at the end. So the final answer to this is actually going to be -7. Okay, so you have to be a little careful if you have a negative out front. Does that make sense? So if you take the absolute value of a negative number, it becomes positive. If it is 0 or already positive, it stays positive. Okay, and then I want to do one more thing in this section. So the last thing I want to do in this section is I want to compare signed numbers. I want to, compare two numbers that are signed and determine whether one is greater than or less than the other one. So comparing signed numbers. Okay, so basically what you do is you compare the numbers on a real number line. A number to the right is larger than a number to the left. Okay, so what do I mean by that? Well, let's do some examples here. Let's say we want to put in the correct inequality symbol meaning either less than or greater than Okay, so this one means less than. I'm reading left to right, and this one means greater than. So we want to put in the correct inequality symbol to make each statement true. Okay, so let's say I want to compare 4. So I have a box. That's where I want to put in my inequality symbol inside the box to 5.5. Let's say I want to compare -1 to -4 fifths. And then maybe actually let's do square root of 2 to 1.2. Negative pi to negative square root of 16. And then I'll do a couple more. Let's say 100, 1 over 100 to 1 over 1,000. And then maybe 9 compared to -22. And then I'll do one more, maybe 1/3 compared to 1/4. Okay, so let's look at what's going on here. In the first example, right, so I'll start over here. 4 compared to 5.5. If you look at a real number line, right, so here's my real number line. So 1, 2, 3, 4. Here's 4. Here's 5.5. So since 4 lies to the left of 5.5, right? We're comparing, we're finding their like relative locations. 4 is to the left of 5.5. Therefore, 4 is less than 5.5. If I compare -1 to -4 fifths, well, -1 is right here, right? This would be -1. -4 fifths, well, I'd have to split this up into 5 intervals. And then -4 fifths would be like right here. So since -1 lies to the left of -4 fifths, it is also less than, right? So -1 is less than -4 fifths. What about radical 2 to 1.2? Well, remember, radical 2 is approximately 1.41. So how does 1.41 compare to 1.2? It's greater than, right? It would lie to the right on a real number line. What about negative pi compared to negative, this should be a 16 here. Negative pi compared to negative 16. Well, negative pi is around negative 3.14, dot, dot, dot. Negative 16 is a perfect square, right? We'll talk about this later on in one of the last sections, last modules. But square root of 16 is exactly 4, because 4 times 4 equals 16, so this is just -4. So how does negative 3.14 compare to -4? Let me draw this out here. So if this is our real number line, let's say 0, I'll kind of make it larger here. So -1, -2, -3, -4. So this is -4. And then this is negative pi, right? Around here would be negative 3.14. So, and I want to compare negative pi to -4. So negative pi lies to the right of -4. So this is going to be greater than, right? So negative pi is greater than negative square root of 16. What about 1 over 100 compared to 1 over 1,000? Again, I'll see if I can draw, kind of expand this out. Let's say here's 0. They're both positive, right? Here's 0, here's 1. So 1 over 100 is very, very small. I'd have to split this up into 100 little pieces. Let's say it's like, this is, I'm not exactly drawn to scale, but let's say this is 1 over 100. 1 over 1,000 is if I split this up into 1,000 pieces and it's just 1 to the right of 0. So that would be like right here. Very, very small. So since 1 over 100 is to the right of 1 over 1,000, it's going to be greater than. Okay, 9 compared to negative 22. Well, 9 is positive, negative 22 is negative. So this one is definitely greater than. And then 1/3 compared to 1/4. Actually, let me use the same. Let me use the same real number line here. So 1/3 is if I split this up into 3 pieces, right? So that would be like right here. And then 1/4 is if I split it up into 4 pieces. So it would be like half, half, half. So 1/4 is like right here. So since 1/3 lies to the right of 1/4, it's greater than. So this would also be greater than. Okay, so when you compare real numbers, right, all you're doing is you're thinking about a real number line, and if a number lies to the right of the number you're comparing it to, it's greater than. If it lies to the left of the number you're comparing it to, it's less than. Okay, and then let's finish up this section by doing a couple of problems from My Open Math. So in this first problem, we just want to insert the correct inequality symbol, whether it's less than, greater than, or potentially equal to as well. So on the left-hand side, I have negative absolute value of negative 14. Okay, so forget about that first negative. We have to do this first. What's the absolute value of negative 14? Well, the absolute value of negative 14 is positive 14. Right? Remember, the absolute value is defined to be the distance from 0 on a real number line, and negative 14 is 14 units from 0 on a real number line. Okay, the easiest way to think about it is if it's negative and you take the absolute value, it's going to make it into a positive number, right, but the same magnitude. But we still have that negative out front, so that negative has to be attached at the end there. So this is really negative 14 on the left-hand side. And I want to compare that to positive 14. Well, certainly negative 14, if you look at the number line, right, this is 0, negative 14 is over here somewhere, positive 14 is over here somewhere. Since negative 14 lies to the left of positive 14, it's got to be less than. So this should be less than. So negative absolute value negative 14 is less than positive 14. Here's another example. Same sort of thing, right? We want to put in the correct inequality symbol or potentially an equal sign. But in this case, we're comparing negative 19 to negative 8. So again, if you think about a real number line, if this is 0, negative 19 is, say, way over here, negative 8 is maybe here. Since negative 19 lies to the left of negative 8, it must be less than. So that would be less than. Okay, great. So what we'll do next in the next few sections in this module is we'll start operating. We'll start doing things with the sign numbers, like adding them, subtracting them, multiplying, dividing them, and so on. Great, thanks.